All right. Seriously, I need to like end physics like 10 minutes early so I can like breathe before I start class here. Yeah, no kidding. That's what I should. I got to the last example in physics. I was like, should I do it today? Should I not? I should have opted to not. So.
Is it physics 1 or
Physics 2. All right. So I do have something to give you guys, if I can find it. So here is a copy of Mission 1. I may not always do this. Well, you know what? Let me always do this for you guys. There's not many of you, and I'm not putting white space. So I should be able to print the thing out for you. And just because I made the mission double-sided doesn't mean that you should make your solution double-sided. In fact, I was actually going to print it single-sided just to make this point, but oh well. Now here's the course guide. Woo-hoo. One for each of you. All right, 2, 3. Don't worry, since I'm starting class late, I will go over. You're like, you're starting class. I know, but I haven't done math yet, so it hasn't started. So, and here is the attendance sheet. I will eventually top hat. I just haven't figured out how to do it yet this semester. I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, I thank you for this class and this opportunity we have just to meet and understand a little bit more about your creation. Help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So a quick correction here. The so if you've already done problem 2, I'm so sorry, but I do need to change it because it's too boring right now. Because problem 2 and problem 1 are like the same problem without me making a change. But you want me to make a change so that we can learn something from the problem, right?
Actually, they're not exactly the same.
Well, they're not literally exactly the same, but they could be solved by the same technique, so they're kind of the same. So what I wanted to do is in this problem 2, where we have x plus 4y, I would like you to take that 4 and make it a 5. If we make that a 5, it becomes more interesting. All right, so there's that. Now, so let me get into it here. So last time I introduced like our notation for matrices, and we talked a little bit about Z mod n, how to calculate in there. It was pointed out to me there's an error in my definition 1.11, like in the second row. If you look at it, I have A21, A12. Obviously that should be A22 and A2n on page 2. Like my enumeration of the components has a typo in it. You can guess who found that. Let's see here. I'm just joking. I am grateful for these kinds of comments. So I wanted to do a couple of different things today. First, I wanted to talk a little bit about like mathematical induction. So what's mathematical induction? I think you guys know from Math 200, right? But I think it would be good for us to do an example, a couple of examples that involve this kind of thinking. And we'll start out with something that's relatively like familiar perhaps. So example 1, if we have A1, A2, A sub k, well, let's say A sub n, invertible, then A1, A2, an inverse is equal to an inverse A2 inverse, A1 inverse for all n in the natural numbers. All right. So this is, anytime we have some kind of claim that's true for all integers, all positive integers, mathematical induction is a rigorous tool we can use to establish the truth of such claims, right? Now, we don't do induction for every last thing we talk about in here that involves this kind of claim, but on occasion we will. All right, so like this one, let's work it out. So I'm going to say that this is my induction claim. I'm going to label it Pn, right? And so mathematical induction works like this. N equals 1. Then P1 is true since A1 inverse equals to A1 inverse, which is, yeah, there you go. So the base case here is kind of silly. All right. Now, suppose inductively that n, well, that Pn is true for some n in the natural numbers, right? Consider the n plus 1th induction claim, right? So what we're going to do is we're going to consider an plus 1, an, oh my bad, I can't. Sorry, I'm putting the, like I said, I need to take a break between this class and physics. Stupid physics. All right, I'll calm down here in a second, eventually. Maybe I need to drink more coffee. All right, so at least it's not 8:15. It could be worse. Like A1, A2, da da da, AN plus AN, AN plus 1, right? Let's invert this thing. Okay? So I would point out that this, we could label all of this, right? Well, all of this, let's say, as, I don't know, let's call it A without an index, right? So this is an plus 1 inverse. And at this point, I realized that stylistically this would have gone way better if I had said, you know, we don't logically need to do it, but we should have looked at the n equals 2 case, right? But you guys know the n equals 2 case already. So let me just say, from Math 221, for the sake of not cluttering up this proof, we know that AB inverse is what? B inverse A inverse, right? The so-called sock shoes rule for inverses. Now, to give a complete proof, we should prove that as well, right? But let me not do that at the moment, if you can forgive me for this omission. So since we know that, we can apply it here, right? And this is what? An plus 1 inverse A inverse, right? By 221. But then by the induction claim, this is an plus 1 inverse times what? Times an inverse dot 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 a2 inverse a1 inverse, right? By induction hypothesis. So what have we showed? We've showed that Pn implies Pn plus 1 is true. Therefore, the claim is true for all natural numbers. This is true by mathematical induction, right? This is proof by mathematical induction. Yeah.
Wouldn't you need to assume the claim retractor to go from the second to last step to the last step? So would you have to iterate through
I'm sorry, I don't quite follow your question yet, Sam. What?
So without further proof, it's not necessarily true that A inverse is AN inverse dot 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 A2 inverse, etc.
That's by the induction hypothesis. So I'm using the induction hypothesis to trade this for that. Because I'm assuming that Pn is true. Pn being true means that if I invert a product of n things that are all invertible, it's the product of the inverses in opposite order. That's the claim. So yes, I do need to use the induction claim, and I am. That's why I say this. And the mark of a good induction proof is that the student has meaningfully said by the induction hypothesis at the appropriate time and place. If your induction proof is missing these words, it's probably missing some points. Right? So yesterday I joked that maybe you'd never prove the sum of the sum is the sum of the sums. Let's prove it. Yeah? So another thing that we actually might need induction for is the finite sum, right? So the definition, if A1, A2, dot, 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 AN are elements of R, where N is an element of the natural number. In other words, what I'm trying to say is, I don't really want to put N here, but let's just say dot, 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 dot. Oh, I know I could just say, duh. AN is an element of R, where N is an element. So like, in other words, we have a list of numbers. And actually, I don't want to just have, oh man, I'm sorry guys, I'll get it eventually. Let's say J, and let's say A sub J, B sub J, there, that's better. So what I want to talk about is a list of numbers from a commutative ring with identity, like we were talking about last time. In other words, it's a context in which we can add and multiply, okay? And, all right. Then we define the sum J equals 1 to 1 of A sub J as equal to A1. And we define the sum of J equals 1 to N of A sub J is equal to A sub N plus the sum J equals 1 to N minus 1 of A sub J for N greater than or equal to 2. This is the recursive definition of the finite sum. So if we want to prove something about finite sums, this is the thing to use. Right? So with this definition in mind, I can make a claim. So my claim is this. My claim is that the sum J equals 1 to N of A sub J plus B sub J, right? Parentheses here, is equal to the sum J equals 1 to N of A sub J plus the sum J equals 1 to N of B sub J for all N in the natural numbers. This is a claim based on an arbitrary natural number. So what proof technique are we going to use here? I think you can guess. We're going to use proof by mathematical induction. So let's give it a name. PN. All right. Sorry, I'm kind of boring. So proof. Let's consider n equals to 1. Well, if we look at the sum, J equals 1 to 1 of A sub J plus B sub J, then by definition, what is this equal to? A sub 1 plus B sub 1, right? Which is, by definition, sum J equals 1 to 1 of A sub J plus the sum J equals 1 to 1 of B sub J. So, by definition of the finite sum, therefore, P1 true. So we have established the base case of the induction, right? Yeah. So then what do we do? Well, same thing we always do. Assume inductively. Assume Pn true inductively for some n in the natural numbers. And then we'll consider, well, you know what we're going to consider. We're going to consider the n plus 1th claim, right? So we're going to look at the sum J equals 1 to n plus 1 of A sub J plus B sub J, right? And by definition, that's going to be a sub n plus 1 plus b sub n plus 1, parentheses, plus the sum, parentheses, j equals 1 to n of a sub j plus b sub j. That is what? That is by the definition of the finite sum. This is the recursive definition of the finite sum. Now, what are we going to do? How can we make progress on this expression? Yep.
Split it up into, well, we know by the inductive hypothesis that the nth case can be split up into two summations.
Okay, so we're going to do that. J equals 1 to n of a sub j. And I like the word you just used there. You said by the induction hypothesis. That brings a tear to my eye. It makes me joyful. It makes me hopeful for the future in here. By definition, well, that's bad. Like, see what happens when I talk and write. Idiot. Me, not you. By induction hypothesis, right? Or you could just say, because Pn be true. And then we're going to do what you were going to try to tell me, which is to regroup terms, right? So if we regroup terms, because addition's associative, as it evidenced by the fact that I haven't written a bunch of cumbersome parentheses to indicate the order of operations here, because who does that? Maybe computer scientists. They care a lot about that kind of thing, I suppose. But that's their business. So regrouping things, we have that and that, right? But then what's the finishing blow here is that is, of course, the sum j equals 1 to n plus 1 of a sub j plus the sum j equals 1 to n plus 1 of b sub j. So therefore, Pn plus 1 true, and claim follows by PMI, proof by mathematical induction. Short on time on a test, there's a way to convince me I know what you're doing without you writing a lot of stuff. Of course, if you just say by PMI and just like write that, it's like, it's not going to, I mean, I'll laugh, but I'm still going to take all your points. Except for one. If I laugh, I give you a point. But don't spend like 10 minutes drawing a dinosaur to try to convince me to laugh or something. It's not cool. Anyway. In your homework, I asked you something similar, very similar, except what I did in the homework was I put a constant here. And I asked you to prove the same claim, but with a constant pulled out. So, yeah. Proof would be very, very similar. Any questions? So one of the things that I didn't define last time, and I really should have, because it's kind of important. So definition, a finite R linear combination, I can't spell, combination of objects A1, A2, AK is finite sum. And that follows, like C1A1 plus C2A2 CKAK, which of course we could write as the sum I equals 1 to K of CIAI, right? This is a finite sum, a finite linear combination. Now it's an R linear where, I should be clear, C sub I is an element of R. That's what makes it an R linear combination, right? If C1 equals to C2 equals to equals to CK equals to 0, then we say the linear combination is trivial. Trivial. Also, we say that 0 is formed by an empty sum right? And so like, I thought I put it here. I don't know where maybe I may be putting the cart ahead of the horse here, but I just want to throw it out here. If we say like span of S, all right, that is by definition like the sum I equals 1 to k of ci ai, such that ai is an element of S, ci is an element of R for some k in the natural numbers. And sometimes we put in sub r here to indicate the coefficients are coming from there. Let me put it into words here for you guys. The span of a set is the set of all possible finite linear combinations from a set. The set S could be infinite, but we only take finite linear combinations. That's the rule in here. The other rule, which I think makes this sentence above make more sense, is that if you take the span over R of the empty set, by definition, it's 0. This is a necessary definition so that we don't have to like make special case comments about important theorems as we go on, okay? Let me give you guys an example. Did I do an example? Well, I guess these induction proofs were examples. Let me call them such. Oh, I did. Example 1. This was example 2. Example 3. If you had S was the set 1x, x squared, x cubed, and so forth, right? And I take the span over the reals of S, right? This is the set of polynomials. In X. Because you're only taking finitely many of them, so you never get like a power series. All you get is a finite collection of, you know, multiples of monomials in X. That's a polynomial. Okay? So that's an example of an infinite set where we use finite linear combinations to construct the objects. Polynomials are like probably the most important example of this idea. Which is easier to work with, polynomials or power series? Polynomials, right? Polynomials, we only have to combine finite things. When we replace that finite linear combination with an infinite linear combination, then all of a sudden we have to do analysis, right? But that's not this course. So, now in the theory of Hilbert spaces, which are infinite dimensional vector spaces, there are places where the concept of span is replaced with infinite sums in a meaningful way. But that's a particular context. So in linear algebra proper, we deal with finite linear combinations, even when the set's infinite. All right. So that's it. Now that brings us to the discussion of linear systems. So let's talk about linear systems. If I can find my starting point, it would be lovely. All right. Let me erase some stuff in here. So this is probably your happy place, right? Like solving systems of equations. I know for me, when I took like undergraduate linear algebra, the first course, right? Like by the end of that course, like I really, really knew how to solve equations, you know? And yet I didn't know some of the things I'm about to show you. Because the course that I had was out of a book which was not really well written. And it was missing some really important insights into the structure of solution sets as they relate to the so-called row reduction, or the reduced row echelon form of the matrix. So to recap briefly, if we have a system of m equations and unknowns, how does it go? Give you a really quick summary here. So we start out with the system of equations that has the form a11 x1 a1n xn equals to b1, and this goes on. Eventually you get am1 x1 amn xn equals to bm, right? So what we're talking about here are m equations in how many unknowns? N unknowns, right? M as in mommy, N as in nenu nenu. It's a little Mork and Mindy reference there for you guys. You all watched Mork and Mindy, of course, being that you're all children of the 70s. But it's not really true. Anyway, so of course we soon got bored with this and replaced it with what? The corresponding augmented coefficient matrix, right? This gives us augmented coefficient matrix. Oh, first of all, different things. One way we could do is we could replace this with a times x equals to b, right? Where this is the m by n coefficient matrix, right? And this is, of course, the vector of unknowns, right? X is equal to what? x1, xn. This guy here is the so-called what? Inhomogeneous term. What's that mean? Well, if b is equal to 0, it's a homogeneous equation, right? And then how did we solve this? What do we do? The method to solve was what? We, number one, we form the augmented coefficient matrix A concatenated with B, like so. Step number two, we row reduce that thing, right? And we get rref of AB, right? And step number three, we read off the solution. There you go. That's 221. I mean, that's 80% of 221, right? Something like that. I don't know. Okay, maybe it's more like 50% in my course. But anyway, truth in advertising, I guess. Okay, so let's look at an example, actually. I want to talk about interpretation. So, for instance, we could example 3. I want to write down something that's true, and then we'll talk about some interpretations of it. The reduced row echelon form of the matrix top row 1 0 0 1 0 0, right? 2 2 0 0 1 0. Third row 4 4 4 0 0 1. You work that out, and it works out to 1 0 0 0 1 0 0 0 1. 1 minus 1 0 0 1 half minus 1 half, and 0 0 1 fourth. All right. this is a straightforward calculation. We can do the 3 elementary row operations, right? The row swap, the row addition, the non-zero scalar multiplication, and combinations thereof, right? The elementary row operations get you from there to there. So let's see how much mileage we can get out of this in terms of, like, what does it mean, right? What does it mean? So let me start out with something that maybe is like, I bet you wouldn't have started with this. But I can interpret this as, one way to think about this is if I'm going to solve system AX equals to 0, where this X is an element of, let's get weird, Q6. Ha! Didn't think I was going to do that, did you? So, hey, I don't know, it's apparently an irrational equation, right? You thought it was real. No, it's rational. How would you tell? I mean, somebody need to tell you, right? So, and Q6, right? So that means that this has got 6 columns. 6 columns, right? So how does this tell you the solution to that? Well, the thing about row reduction is it goes column by column, right? So if what's given is true, it's still true if I slap zeros here, right? So one of the things we learned in 221 is we can always adjoin another column of zeros and it doesn't change the story, right? Row reduction works left to right. So anyway, with that in mind, I can see from this that x1 is equal to minus x4, x2 is equal to x4 minus 1/2 x5, x3 equals to 1/2 x5 minus 1/4 x6. So my first interpretation of this calculation is we could look at it in terms of 3 equations and 6 unknowns, and I can write down the solution set, which involves what? 1, 2, 3, 3 free parameters, right? Here, x4, x5, and x6 are elements of the rational numbers, right? These are the free parameters of the solution. What does the solution set look like in this context? Let's write it down. Solution set. It is minus x4, x4 minus 1/2 x5, 1/2 x5 minus 1/4 x6. And then you got your x4, your x5, and your x6, such that x4, x5, x6 are rational numbers. That's the solution set. It's also a really poor way of writing it. A better way to express the solution set is that it is the span over the rationals of minus 1, 1, 0, 1, 0, 0, comma, 0, minus 1/2, 1/2, 0, 1, 0, comma, 0, 0, minus 1/4, 0, 0, 1. Is there a trash can back there even? Okay, all right. Now, can you guys recognize this calculation? This is the what? The null space basis calculation. These vectors form the basis for the null space of that matrix. If you don't remember that from 221, it's okay. We're going to get back to it. I just want to point out that that's what this calculation means. All right? There cannot possibly be any linear dependence amongst these vectors, because that's tantamount to saying that there's a linear dependence amongst the free variables, which is, of course, an absurdity. Free variables are free, right? To say there's an interlinking of the free variables would be to say that there's a interlinking of the non-pivot columns. And if that's the case, then you could like, anyway, let me not, they have to be linearly independent. And you always can do this. You can always factor out those constants, right? This is one interpretation of this calculation. What's another? We could also, let me do it in blue, think about this as the augmented coefficient matrix for this system, right? So interpretation 2, three equations in 5 unknowns. Unknowns, I can't spell. Well, let's say in the complex numbers. Haha, you didn't see that coming, did you? And so if that's the interpretation, we can read from this, our system of equations, the solution is what? x1 is equal to what? Minus x4. That's it. x2 is equal to, it's pretty much the same as I did before. What's the difference? Well, yeah, I guess you could write plus 0. I wasn't going there, but that's also true. We will omit the plus 0 i's. Yeah, they're there. It's kind of like wings on an elephant, right? They're just set to 0. So I learned that joke in graduate statistical mechanics, but no, wait a minute, no, solid state physics. x3, but the professor had a really bad stutter, so it took me a long time to understand the joke. He says, the elephant has wings. What can you say about them? Like, what's he saying? This is in the middle of like a serious solid state lecture. Like, and then finally it was like, oh, he's telling a joke. Dang it. So 1/2 x5, the x6 is not here anymore, right? So it's like 1/2 x5, and then plus 1/4. And so if you were to write the solution set, it would be the span over the complexes. If we work through it, everything works the same, except what? That right there, right? Plus what? The third one got a quarter in it. And I think everything else is 0. So if these 3 equations and 5 unknowns, if we write them as like, let's say, well, I wrote AX up there, so let's say BY equals to, well, oh, B is an unfortunate. Let me, instead of using B, let me say MY equals to like B, right? This guy right here would actually be what we call the null space of M, right? And this character right here is what we call a particular solution. In other words, anything in here would have the property that like M times like, you know, Y equals to 0. If Y is an element of this, My is equal, anything in here multiplied by that matrix. This matrix right here is what I'm calling M, right? Anything in that time, anything in here times that M would be 0. And if I take this thing times M, I get 0, 0, 1. So this particular solution would give us M times Y, let me call this YP for particular, MYP equal to, you know, 0, 0, 1. That would be the meaning of this term over here. And you can check me on that, right? If you multiply this by that, you get 0, 0, 1, like I claimed. Yeah.
In that span, where are you getting the 0, 0, -1/4, 0, row for the third one.
Right here. Where's it coming from, though, is like, oh, wait a minute, did I have an error?
But isn't that sort of representing x that...
Hold on,
doesn't
hold on.
that come from x6, which doesn't exist in this case?
You're right. I was supposed to do what? Oh, it's worse, right? So what do? This is easily fixed. This is a wonderful question to have asked me during class. Thank you for asking this during class. Very helpful. There we go. Now, how could we have expected that? Yeah.
Because the sixth variable has pretty much become the extra particular solution.
That's a good way to think about it. There's like a theorem we learned, right? The rank nullity theorem. It said the number of columns in the matrix, it's equal to the dimension of the null space plus the rank. Now the rank here is clearly 3 because these are not like, because there's, oh no, ow, I'm sorry. Well, bonus point, I guess. Well, the rank is 3 because you got 3 pivot columns, right? So the rank is 3. So if the rank is 3, the dimension of the null space has to be 2 because we've got 5 columns in the second interpretation, right? So I should have seen that. If I was thinking about rank nullity, I knew I made an error. Can you guys tell me any other interpretations of this calculation that we could go through? Maybe the first one you've probably thought about. As soon as I wrote it up there, it was what? What does this calculation mean? Yeah.
You just found the inverse.
Right, we just found the inverse of the 3 by 3 matrix. That's exactly right. And let me try to unwrap that. What is the inverse matrix problem anyway? So let's think about this. The inverse matrix problem if we have we want A times A inverse to equal to the identity matrix, right? But the identity matrix is E1, E2, En, right? And so if we call A inverse V1, V2, Vn, right? Then by the column by column multiplication rule, this is AV1, AV2, AVN. So you see, these two things being equal means that what we're trying to solve is AVJ equals to EJ for j equals 1 to n. In other words, to find the inverse matrix, we have to solve n problems of n equations and n unknowns simultaneously, but they've all got the same coefficient matrix, right? Which means that when you do the row reduction on the coefficient matrix for these n different problems, it's all the same. So you might as well just do it all together, right? You can do a single row reduction to solve all of these systems at once. And that's what we do. Like, that's why you do rref on A concatenated with I, because that is what? That's A with what? E1, E2, En, right? So this is called a super augmented matrix. Every one of these systems we would solve by the same set of row reductions, right? If the inverse exists, it must be that there are n independent columns for this square matrix A, which means this has to reduce to the identity matrix, right? And, you know, the V1s that we're trying to find. Oh, wait a minute. Well, just a second. Yeah, the V1s. Sorry, get ahead of myself. Anyway, you guys know this. You learned this algorithm, right? But it would be good for you to understand why it's true as well, right? It's because if we want to solve more than one system of equations that have the same coefficient matrix, we can do it all at once, right? Like I could solve 2 problems at once with this problem, with this right here, right? Can I erase what I've done so far? Check this out. I'm glad that I'm erasing this after your comment. Because like if I just erased this and then you're like, I had a question, and I'd already erased that part, you know, that would have been truly miserable. So let's put the dividing line like right here. If we did that, then we could ask the question, you know, if I call this matrix, I guess I'll call it, what I used A, I haven't used B yet, have I? So I'll call that big B. So we're asking the question, like, does BZ equal to 0, 1, 0? Does BZ equal to 0, 0, 1? We're answering both of those questions at once with this calculation. And the answer is, this has solution Z equal to, well, let's see here. So it's 4 equations, right? So I got like Z1 equal to minus Z4, Z2 equal to Z4 plus 1/2, Z3 equal to 1/2. See that? That comes from this right here. Yep.
The bottom one, Z3 be negative 1/2.
Yes. Thank you. Muchas gracias. And then this other one would be like the same business for this, right? So this one would have solution like Z1 equal to minus Z4, Z2 equal to Z4, Z3 equal to 1/4, right? That would be the solution to that problem. We've solved both of these equations with that one row reduction. This is the idea of the super augmented matrix. All right. That may or may not have been covered in my undergraduate linear course. I don't remember. There's more though. There's something else. There's something deeper here, which I should tell you guys about. That's actually really, really critical for us from a calculational perspective. All right. And that is the so-called column correspondence property. All right. So the column correspondence property is what? What's the column correspondence property say? The CCP. It says that any linear dependence among the columns of a matrix will also be found in any row equivalent matrix. Now my brother's proof of this is simply the following statement. Row reduction never mixes columns. Proved. But I prove this by multiplication. I prove this by, I look at a linear dependence in the original matrix, I point out that the row reduction can be accomplished by multiplication by an elementary matrix. So I can take the linear combination, multiply by the elementary matrix. That gives me the corresponding linear combination of the row reduced matrix. And that's why this is true, because elementary matrix multiplication accomplishes row reduction. Like, that's another way to say it. But so like here, why is this useful? This is useful because if there's any linear dependence amongst the columns, it is manifestly obvious in the Gauss-Jordan eliminated form, right? In the rref. In the reduced row echelon form of the matrix, if there is any linear dependence amongst the columns, it is manifest. First of all, there is no linear dependence amongst the standard basis. You're not in the reduced row echelon form until your pivot columns are E1, E2, ... ek, where k is the rank of the matrix, right? This has rank 3, E1, E2, E3. What comes past that, right, or in between it, must be non-pivot columns, and those have to be linearly dependent on the pivots. Like this one, column 4 is equal to what? Column 1 minus column 2, right? And let's see, what else can I tell you here? Column 5 is equal to 1/2 column 2 minus 1/2 column 3, yeah? And column 6, what can we tell me about that? Well, column 6 is apparently 1/4 of column 1. These are linear dependences, which you can see between the original matrix. First of all, I find these linear dependencies by inspection of the rref, of the reduced row echelon form. But these will also be true for the original matrix. Yeah?
Real quick, column 6 shouldn't be 1/4 of column 3.
Oh, yeah. Good, you guys, so did Majeric teach this? Good, okay. Because it's not really like emphasized by the book. But I want us to learn it in 221. Can you see why? I mean, does this make, this one's perhaps the most surprising one. 1/2 column 2 minus 1/2 column 3. 1/2 column, so that's like what, 0, 1, 2 minus 0, 0, 2 gives us, what was I doing? Oh, no, it gives us, 1/2 is 1, 0, 1, 2. And then I subtract 0, 0, 2, and I just get 0, 0, 1, right? But I don't know. This is very, very important, very useful. The only thing I haven't covered in chapter 1 is like, there's like a page I talk about homogeneous solutions versus particular solutions. It would be good for us to go over that, but I really don't want to clutter next class with that, so I'm just going to let you guys read. If you'd read chapter 1, whatever we'll come back to this stuff as we go through examples, but Friday, I will define vector space and we'll start this material properly. I mean, that's where this course, we need these things, of course, but vector spaces is really the first properly 321 topic. Thanks, guys.